In this lesson that covers two sections in the book, we'll briefly talk about Rolle's theorem and the mean value theorem, and then we'll look at what these things imply about how the derivative is related to the original function. First off, Rolle's theorem, and I'm going to kind of go through this theory a little bit quickly. If you're a math or computer science major, you should definitely read this very carefully. But for all the theorem stuff in here, I'm just going to kind of give you guys the idea of here's what's really going on. If you've got a function that's continuous and differentiable, and you have endpoints that have the same value on that interval, then you are guaranteed to have a number in the center of it so that the derivative is 0. This theorem tells us that we are guaranteed to find a place where the derivative is 0, which could be an absolute max or an absolute min. Let's use an example. We're going to show that this function has a value so that f prime of c equals 0. We need to quickly state, yes, it's continuous and differentiable. It's a polynomial and we can assume that immediately. So continuous and differentiable are good. The function has a value c. Well, the next thing that we need is that f of a equals f of b. That will certainly be the case at the two x-intercepts, but just to check this, let's make sure that there are two x-intercepts by setting this equal to 0. Notice this is x minus 1 times x minus 3. So if I set each one equal to 0, I get 1 and 3. So thus, f of 1 equals f of 3. They both equal 0. By Rolle's theorem, we get there is a c between 1 and 3 such that f prime of c equals 0. So that's the statement of Rolle's theorem. Simple enough. Let's continue. Next example with Rolle's theorem. We want to show that there is such a c for Rolle's theorem, and then find it between -2 and 2. Continuous, I'll abbreviate this, and differentiable are check. It's again a polynomial. This time what we're going to do is we want to simply show that there is a c in -2 to 2 so that the derivative is 0. Now, I will point out that -2 and 2 should both have the same value in here because these are both even powers. So I'm guaranteed there is one by Rolle's theorem. But if we want to calculate this, let's just go ahead and find out what f prime of x is. Looks like 4x cubed minus 4x. So if we want to show that or find the c that's in there, we'll do f prime of c, which is 4c cubed minus 4c, set it equal to 0. Factoring out 4c, I get c squared minus 4 works. And so I get 4c equals 0, or c squared minus 4 equals 0, which gives me c equals 0, c squared equals 4, and thus c equals plus or minus 2. 0 is the value that lies strictly between -2 and 2 that is guaranteed by Rolle's theorem. Let's continue. I don't want to spend a lot of time on this section just because this is more of a theoretical section. Next one is the mean value theorem. The mean value theorem is a lot like Rolle's theorem in that you do need continuous and differentiable, but in this one, instead of just being said, well, if they're equal, there's a value where f prime is equal to 0, instead we can immediately say there's a value where f prime of c equals this quantity. Now this quantity is what we call the average rate of change. So let me just give you a little picture. Let's suppose we've got a and b right here. F of b minus f of a over b minus a is the slope of the line between them. What mean value theorem says is we are guaranteed to have a c so that the value there, the slope of the tangent line, has the same slope as the average rate of change. That's all this is. And this is actually very helpful for what we're going to do in the next section. Let's continue. Let's do the same thing. We're going to say, yes, this works from 1 to 4, and then find the values of c that satisfy this. So this is going to be a little bit more work, but we can do it. First off, we do need continuous and differentiable. All I got to say to that is true. And there is a bit more to it as to why it's true, but if x were 0, we'd have a problem. 0 is not in here, so we're good. Let's calculate the derivative. F prime of x equals, well, 4 is going to disappear entirely. We might make a comment that f of x is equal to 4 minus 4x to the negative 1, because that'll make it easier to take the derivative. I've got negative 4. X to the negative 1 becomes negative 1x to the negative 2. Consequently, the derivative is 4 over x squared. The mean value theorem says that the slope will have a value in 1 to 4 so that it's equal to the average rate of change from 1 to 4. We need to calculate that. We need to calculate f of 1, f of 4, and the rate of change f of 4 minus f of 1 over 4 minus 1. F of 1 is 4 minus 4 over 1. That's definitely 0. And then f of 4 is 4 minus 4 over 4, which is 3. So we have 3 minus 0 using those numbers over 3. That's equal to 1. Finally, f prime of c is going to be 4 over c squared. And the mean value theorem says this has to equal 1. There is a value that will equal 1 in the interval from 1 to 4. Multiplying both sides by c squared, I get 4 equals c squared. So c equals plus or minus 2. And sure enough, one of those is in 1 to 4, namely the positive 2. This is a little application of the mean value theorem. If you have an average rate of change, and in this case we're going to calculate an average speed, you are guaranteed that at some point that object went the actual average speed. Because distance and velocity is a continuous function, we're talking about over time. Time doesn't have breaks or gaps where you're just going to suddenly teleport to another location. Two patrol cars are 5 miles apart, and the speed limit is 60 miles per hour. A truck passes the first car. 4 minutes later, it passes the second car. Should the driver be given a ticket? All we need to do is figure out the average speed that the car went. You note that speed, or rate, is equal to distance over time. The speed was, well, 5 miles divided by 4 minutes. We're being given a speed limit of 60 miles per hour, so let's convert minutes to hours. We know there are 60 minutes in 1 hour, so the minute units cancel, and we get, I see, 75 miles per hour. By the mean value theorem, which I usually abbreviate, the truck traveled 75 miles per hour sometime between the two cops. Thus, by the book, he should get a ticket. Let's move on to the new material that's much more relevant to what we're going to do. Here's the concept of increasing and decreasing functions and how everything fits together. Function is increasing or decreasing based on these criteria. If you've got two numbers with x1 less than x2, then the function value at x1 is less than the function value at x2, meaning the function is going up as x gets larger. But for decreasing, if x1 is less than x2, then x1's function value is greater than x2's function value. So as x gets larger, the function is shrinking. That's the idea of decreasing. Here's a beautiful theorem to put all this together to what we have. If a function's continuous and differentiable, then what we have is that if the derivative is greater than 0, the function's increasing. If the derivative is less than 0, the function is decreasing. And if the derivative equals 0, the function is constant. That's a handy thing to know. I want to give you guys a little proof of this, but what I'm going to do is write the whole thing, and then I'll come back and explain it. What we do is if we want to show that the function is increasing, and we're assuming the derivative is greater than 0, we choose an x1 and an x2, and we want to show that f of x1 is less than f of x2. We can use the mean value theorem that we just got from the previous section to say that there is a place where the derivative equals the average rate of change. But by our assumption, we know that f prime of c is greater than 0, so the average rate of change is greater than 0. Multiplying both sides by x2 minus x1, which is not 0 because of this setup, we get that the numerator is greater than 0. Add f of x1 to the other side, and we did indeed show f of x1 is less than f of x2, therefore the function's increasing. And the other ones are very similar. It's not hard to say that if all of this works out, with the derivative being positive we get increasing, derivative negative we get decreasing, and derivative 0 we get constant. We can use this every time. This is a way that we can find out if a function is increasing or decreasing. The function might switch from the derivative being positive or negative if it goes through 0 or if it goes undefined. Now that makes perfect sense. You cannot switch from a positive or negative number without going through 0. You have to pass through 0 to switch from positive to negative, or perhaps the function will just stop having a value at all, in which case we better check between those. When the derivative is 0 or undefined, that's exactly what we called a critical number. We'll look at the critical numbers, and what we're going to do is create intervals around them. We'll check a test point inside those intervals, and then simply say, is the derivative positive or negative? If the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. Let's do an example to solidify this. We've got this function f of x, and I want to calculate the derivative. F prime of x equals 3x squared minus 6x, and I'm going to find the critical values. The derivative is defined everywhere, so I simply set it equal to 0, and I'll factor out a 3x. 3x is 0, or x minus 2 equals 0. I get x equals 0 or 2. Those are my critical values. So here's how I do this. I plot the critical values on a number line. And what I'm going to do is I cannot have the function switch from increasing to decreasing without going through these values. So if I check any point in that interval and find that it's increasing or decreasing there, then it's increasing or decreasing on the whole interval. It can't change because there's no place for it to change. It will stay either positive or stay negative. I will pick some test values. And I just choose something convenient between the intervals. It is important that it's not at one of these numbers. So I looked at -1 is less than 0, 1 is between 0 and 2, and 3 is greater than 2. Here's where it's a little different than what we did in the last section. We're going to test them in the derivative. I want to know if the function is increasing or decreasing there. F prime of -1 is 3 times -1 squared minus 6 times -1. That's 3 plus 6 is 9. That's greater than 0. So therefore the function is increasing from -infinity to 0, everything less than 0. Next one is 1. I get 3 times 1 squared minus 6 times 1, which is -3, meaning the function is decreasing between 0 and 2. Finally, plugging in 3, I get 3 times 3 squared minus 6 times 3. That's 27 minus 18 is 9. Since that's positive, the function is increasing. Our test points gave us increasing, decreasing, increasing. Let's just write our final answer. The function is increasing on -infinity to 0, union 2 to infinity, and it's decreasing only on 0 to 2. Again, find the critical numbers, put them on a number line, choose test points, and plug them in the derivative. Where the derivative is positive, it's increasing. Where the derivative is negative, it's decreasing. This gives us information about when the function is increasing and decreasing. Now we can talk about relative maxima and relative minima. We finally have enough. This is what we call the first derivative test. And it's a simple test. If the derivative changes from negative to positive, the function has a relative minima. And I can draw you a nice simple picture. If we go from decreasing to increasing, that's a relative minima. Switch from negative to positive, you will have a minimum there. But if we switch from positive to negative, we get a relative maxima. And then if it has the same sign, such as this or this, then it's neither a relative maximum or a relative minimum. That's it. If the function switches from decreasing to increasing, it's a min. If it switches from increasing to decreasing, it's a max. Otherwise, we drop it. This is where we finish off what we were doing a minute ago. This number 4 is to the previous list and not this one. Once we've got our critical numbers, we found where it's increasing and decreasing, we simply look. If it switches from decreasing to increasing, there's a min. If it switches from increasing to decreasing, there's a max. Let's do a few examples of this. And let's figure out where the functions have increasing and decreasing, and also the relative maxima and relative minima. First, take the derivative of the function. We get 2x minus 4. Now we need the critical values, so I'll set that equal to 0, getting me 2x equals 4 and x equals 2. We have a critical value, and we put our critical values on a number line. Then we pick test points. To the left of 2, I'm going to pick 0. That's always a great choice. To the right, I'll pick 3. Now, where do we put the test points? In the derivative. Remember, for increasing and decreasing, you plug them into the first derivative. The derivative was 2x minus 4. So I get negative 4 for the first one, and I get 2 for the second one. Remember, negative means decreasing, and positive means increasing. The function is increasing from 2 to infinity, and decreasing from negative infinity to 2. The relative max, well, let's find out. Is there one? No. It could only occur at critical values. And this one, this critical value, goes from decreasing to increasing. You can even look at the picture. That's definitely a minimum. None. Relative minimum. That occurs at 2, and I actually do not have the y value yet, do I? How do I find it? What function gives me the y value? It's the original function. If you're trying to find the y coordinate, after you've done all the work to find where the max and the min is, the y values come from plugging it back into the original function. I'm going to just come over here and calculate f of 2. F of 2 is 2 squared minus 4 times 2, which is 4 minus 8, that's negative 4. And that completes the question. We've got a cubic function. So again, start off with the derivative. I get 6x squared plus 6x minus 12. And if I'm going to set that equal to 0, I'll factor out a 6 first. So I get 6 times x plus 2, x minus 1 equals 0. Now the 6 has no bearing on my answer, just divide it out if you want to. Whatever the case, I get negative 2 and 1 for my critical values. Plot them, negative 2 and 1, and choose test points. 0 is always a good test point. Negative 3 will work for the left of negative 2, and 2 will work for the right of 1. Always choose a test point between and around all your critical points, and then we'll plug them in the derivative. Remember, the derivative is used for increasing and decreasing. The function is used for y values. So let's calculate all these. F prime of negative 3 is 6 times negative 3 squared plus 6 times negative 3 minus 12. That's pretty big. Let's see. Negative 3 squared is 9. 9 times 6 is 54. 54 minus 18 is 36. And 36 minus 12 is 24. Next one is 0 squared plus 6 times 0 minus 12. That's pretty clearly negative 12. Oh, by the way, that means increasing at negative 3, decreasing at 0, and at 2. I get 6 times 2 squared plus 6 times 2 minus 12. That's 24. Plus 12 minus 12 is 24 again, so that is increasing. Now, let's write down our answer. Increasing happens everywhere where I got a positive derivative. Negative infinity to negative 2, union 1 to infinity, and decreasing occurs from negative 2 to 1. Now let me warn you guys on one thing. This negative 3, the 0, and the 2, notice they did not show up in my answer. These are test points. These test points simply tell me, is the derivative positive or negative on that interval? When I write my answer, my critical points are in my answer, not my test points. Relative max. Let's see. Is there a place where it went from increasing to decreasing? Yep. Negative 2. Relative min. Is there a place that it went from decreasing to increasing? Yes, it happened at 1. So let's find our y values and we're finished. Plug it into the original function for the y values. G of negative 2 is 2 times negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2, 20. So 20 is my relative max's y-coordinate. And then g of 1 will be a little bit easier. So 2 times 1 cubed plus 3 times 1 squared minus 12 times 1. 2 plus 3 minus 12 is negative 7. So that's my relative min. There you go. Last one. Take the derivative. Now let me show you guys a little trick. Remember, if there's a number in the numerator or denominator, you don't need the quotient rule. That's like a 1/5 in front. It's a constant multiple. Leave it there. So x to the 5th becomes 5x to the 4th. The 5x just becomes a 5, and so my derivative is x to the 4th minus 1. If I set that equal to 0, I can factor this. I get x squared minus 1 times x squared plus 1. But x squared plus a number is never going to be 0. Let's just avoid that entirely. Doesn't add anything to this discussion. But if x squared minus 1 equals 0, I get x squared equals 1, so x equals plus or minus 1. So those are my critical values. Negative 1 to 1 goes on the graph. And then test points, I'll choose negative 2, 0, and 2. Again, you get to pick these, but choose 0 if it's a possibility. If one of your critical values is 0, you can't, but 0 is a nice choice usually. Plug them into the derivative to find increasing and decreasing. I'm going to use the x to the 4th minus 1. I get h prime of negative 2 is negative 2 to the 4th minus 1, which is 15. H prime of 0 is 0 to the 4th minus 1, which is negative 1. And h prime of 2 is 2 to the 4th minus 1, which is again 15. Increasing, decreasing, increasing. I should warn you guys of one thing. It's not always the case that it alternates. It may sometimes go increasing and then increasing again. Alright, with that said, let's write our final answer. Increasing is negative infinity to negative 1. Union 1 to infinity, again using my critical points. Decreasing is negative 1 to 1. The relative max, well look, where does it switch from increasing to decreasing? Increasing to decreasing is at negative 1. And the relative min switches from decreasing to increasing at 1. And then to plug these in to the original function, we can get our y values. H of negative 1 is 1/5 times negative 1 to the 5th minus 5 times negative 1. That's negative 1 plus 5 is 4, so I get 4/5. A little bit of a fraction work there, but you guys can handle it. The last one is 1 to the 5th minus 5 times 1, so I this time get negative 4/5. 4/5 goes with my max. Negative 4/5 goes with my min. And this is my final answer.